Welcome back to Simple Gaian. If you are an electrical engineer, a student, or a technician working in a substation, you have definitely faced this confusion. You look at a single line diagram and you see a device labeled PT. Then you look at a modern GIS substation drawing and the same device is labeled VT. You ask your senior, "Sir, what is the difference?" Some say, "Oh, PT is for potential, VT is for voltage." Others say, PT is old technology, VT is new technology, and some might even tell you they are totally different machines. So who is right? In today's video, we are not just giving you a one-line answer, we are doing a 20-minute masterclass on this topic. We are going to cover the real difference between VT and PT, the internal construction, why you can't use a power transformer as a VT, and the deadly safety mistakes you must avoid. We'll also cover advanced topics like ferroresonance and accuracy classes. By the end of this video, you will know more about instrument transformers than 90% of the engineers out there. Let's get started. First, let's kill the suspense. Voltage transformer, VT, and potential transformer, PT, are the exact same physical device. There is no difference in their working principle, their construction, or their function. If you order a 33K5 PT from a manufacturer and your friend orders a 33K5 VT, you will both receive the exact same box. So, why the confusion? It's a battle of history versus modernization. Historically, in the early days of electrical engineering, especially in the USA and standard ANSI regions, the term potential was used to describe electric pressure. However, as the world moved towards global standardization under the IEC, the terminology was simplified. We measure current, so we have a current transformer, CT. We measure voltage, so logically we should have a voltage transformer, VT. Today, VT is the standard term in most modern international specifications. PT is still widely used in India, the US, and by veteran engineers. Both are correct. But for this video, I will use them interchangeably. Now, why do we even need this device? Imagine you are managing a 220,000 volt transmission line. You need to know two things. Is the voltage stable, and is there a fault? You cannot just buy a multimeter and touch the 220 kV line. You would be vaporized. So we need a translator, a device that takes that massive 220 kV and steps it down to a safe, standardized value like 110 volts. The VT does this using the principle of mutual induction. If you have 10,000 turns on the primary and 100 turns on the secondary, your voltage drops by a factor of 100. But here is the catch. A VT must maintain linearity. If the 220 kV line spikes by 10%, the 110V output must spike by exactly 10%. If it doesn't, your protection relay won't trip, and your expensive equipment will burn. While VT versus PT is just a name change, there is a real physical difference you need to know. Inductive versus capacitive. First, the electromagnetic VT. This is the old reliable. It looks like a standard tank transformer with a big iron core. It's extremely accurate and great for metering, but becomes expensive and heavy at high voltages. Once we cross 132 kV, inductive VTs become too expensive. Enter the CVT. A CVT doesn't use a massive coil, it uses a capacitor divider. Imagine a stack of thousands of capacitor plates. The capacitors split the 400 kV down to roughly 12 kV. Then an intermediate transformer at the bottom steps that 12 kV down to 110 V. The secret benefit of CVT is PLCC. Since capacitors pass AC frequencies, we can use the CVT to inject communication signals into the power line, allowing substations to talk to each other. I often ask students, both machines step down voltage. Why can't I just use a small distribution transformer as a PT? There are three critical engineering differences. Difference number one, flux density. A power transformer runs at the knee point of saturation to be efficient. A VT runs at a very low flux density so that if voltage spikes, the core doesn't saturate and distort the output. Difference number two, burden. A power transformer powers houses. A VT powers a meter. We measure VT capacity in VA, typically just 50 or 100 VA. Difference number three, voltage drop. In a power transformer, we accept some drop. In a VT, voltage drop is the enemy. Internal resistance is kept incredibly low, so the output is a perfect mirror of the input. If you sleep through the rest of this video, wake up now. This section saves lives. In a substation, current transformers, CT, and voltage transformers, VT, have opposite safety rules. The rule for CTs, never open the secondary circuit. The rule for VTs, never short the secondary circuit. A VT is a voltage source. If you short the secondary terminals, massive current will flow, melting the windings in seconds. That's why you always see fuses or MCBs on the secondary side of a VT. How accurate is accurate? We buy VTs based on their accuracy class. Class 0.2 is for metering billing. Money is involved. Class 3P is for protection. We care about reliability during faults. Finally, fluorescence. This kills VTs. It happens when the inductance of the VT and capacitance of the line resonate, causing voltage spikes up to 400%. Modern VTs use a damping resistor to absorb this. To summarize, VT, Rs, PT. Use inductive for distribution, CVTs for transmission. Never short-circuit a VT. Use class 0.2 for billing. I hope this masterclass made you a substation expert. If you learned something new, hit that like button. And tell me, what next? Vacuum circuit breakers or SF6? Let me know in the comments. This is Simple Guyan, simplifying engineering for you.